Well, thank you. So it's my pleasure to thank the conference organizers for the invitation and for this wonderful venue and wonderful conference. So HALO and HALO-1 kiloton are supernova detectors. So I'm going to spend just a few minutes talking about supernova neutrinos. They are lead-based detectors, so I'll describe that. HALO is an existing detector at SNOLAB, and HALO-1 kiloton at Gran Sasso is in the letter of intent state. When thinking in the context of making a proposal to spend a lot of time and money, we've identified some risks. I'll mention those along the way and talk about our mitigation strategies, and then give a quick status. So supernova neutrinos, I really cannot do better than our speakers yesterday in terms of describing the theory and the interest, but there's a few generic things to say. And it's not normally said this way. I mean, clearly supernova neutrinos are our window into something very fascinating. And it's also the interior of a core collapse supernova is the only place where matter is opaque to neutrinos, and we have the opportunity to learn something about the equation of state of the protoneutron star, where the neutrino density is such that neutrinos interact collectively with each other and produce new phenomenology that we could observe. And also, it's a corner of the QCD phase diagram, high density and low temperature, that is unexplored and that has potential features in it. So we have a situation where the collapsed core is radiating neutrinos. They travel out. We have some generic expectations in terms of a hierarchy of the temperatures of the neutrinos. As they radiate out, there are collective effects, potentially MSW effects, multiple expected, effects due to shock wave and three-dimensional hydrodynamical effects, and then vacuum oscillations and Earth matter effects before we reach Earth. And nonetheless, with all that complication from 20 or 22 events in 1987, we learned a great deal. So it's not really a simple picture at all. As Christina explained yesterday, there are things happening. This is basically an instant in time. So there are things at this instant in time happening behind the shock wave. The shock wave is traveling out. There are things happening in front of it, multiple MSW resonances, etc. And the vacuum oscillations. I'm repeating a bit what I said on the previous slide. And on top of this, the neutrino emission source is evolving as a function of time. The star is exploding as a function of time. There are large-scale three-dimensional effects occurring that play into that. And then any given detector here on Earth imperfectly records a part of the signal and probably does not end up with the statistics that one would hope for. So the question is, really what can any one detector do when the signal is spread across these species and the time evolution of their flow and energy, etc. And one has marginal statistics. That's a very difficult question to answer. We also have these phases of a supernova explosion. The timescales here are tens of milliseconds, fractions of a second, and then in the cooling phase, seconds. And I don't want to go into the details. It was done better yesterday. But one thing to note is that most of the existing detectors only see the blue line. So the message is that there is more structure anticipated, and generally speaking, we're relatively blind to it. So the real trouble with supernova is that they do not occur that often. Okay, this is an estimate of a Monte Carlo simulation generating supernova throughout our galaxy and asking, would they have been seen, and would that rate be consistent with what was actually observed? There are many other estimates of the supernova rate done in different ways. They tend to have smaller error bars than this. I used to always say 3 plus or minus 1, and I'm an optimist. That was in my lifetime, so here we go. And so even though the galaxy may be a larger place than we previously thought, the universe. Larger than we thought, we're still confined to the galaxy and this low rate. So there are currently 7 detectors participating in SNOOS, and I would hesitate to bet that most of you are familiar with the first 6 and less familiar with HALO. We need to do something about that. With the exception of HALO, all of these are liquid scintillator or water Cherenkov detectors and are dominantly sensitive to the nu bar flux through inverse beta decay. Lead-based detectors, such as HALO and the proposed HALO 1 kiloton, have the nu bar signal really suppressed. I'll discuss this on the next slide. We're basically nu bar blind and hence complementary. The reactions that occur in lead are listed here. Charge current and neutral current with significant thresholds shown there. It's sort of tantalizing to look at the electrons here in the charge current reaction because they potentially carry information about the energy of the neutrinos or could be used to tag the charge current events. However, doing that requires seeing, recording most of the energy from the electrons. And so there have been attempts to look at different ways of getting a lot of lead into solution. One was lead perchlorate, which is an explosive that was discarded. And we've also looked at how much lead acetate we could dissolve in hot glacial acetic acid. That's kind of interesting until you think of a kiloton of hot acetic acid. So we don't see any route there that would allow us to see the charge current and tag it. Any instrumentation that involves, say, fine-grained scintillators really blows up the cost of the detector because it has to be really fine-grained, and most of the cheap scintillator contains hydrogen and it competes with the helium-3 tubes that we're going to instrument this with to see the neutrons. And so that's not really an option for us either. So we are not proposing to tag the charge current events or measure that energy, unfortunately. We think there's merits still to the detector that we can build, and I'll get to those. The neutrons are detected through neutron capture on helium-3 after they thermalize, so with a lifetime of around 200 microseconds. And therefore, we lose all information of the energy and all information associated with the direction. This is really a counting experiment, and we count the 1 and 2 neutron events. If we look at, well, let me say first. So there's a merit to a lead-based detector in that it is very simple, robust technology, and once built, the maintenance is near zero, and it can sit there for decades and wait with near zero cost. You cannot say that about many other detectors. The scientific merit sort of rests on this idea of complementarity of the flavor sensitivity. Okay, complementary to liquid scintillator, water Cherenkov. Not so complementary to DOOM, that's off a bit in the future. This complementarity comes about from the nuclear physics of the lead nucleus, the neutron excess in lead Pauli-blocks the nu bar charge current reactions, and also the high Z sort of further suppresses the nu bar charge current and enhances the nu E charge current. So the response of a lead-based detector is dominated. It's sort of an unresolved mixture of nu E charge current and the non-electron flavor neutral current, orthogonal in some sense to the other existing detectors. For a reasonable set of neutrino average energies here and their corresponding temperatures over here, we get this sort of division of events happening in a kiloton detector. This is at 10 kiloparsecs and assuming 100% efficiency for the moment. The colors across the top are the 1 neutron events. And so to get the 1 neutron events, you sum up the red, green, and blue. And the other are the 2 neutron events. Or if you want to look at the red and the orange, these are the nu-E part, and the rest are the nu-X part. And as you move the temperatures around, the pi diagrams change. Snow globes is a tool that we use to explore the response of our detector without doing a complete simulation of it. So it's for quick studies as we try to get a handle on the physics handles that we could have with such a detector. And the cross-sections that are implemented in there are from Engel, McLaughlin, and Volpe. These are the standards that are used, although I suspect they're standards because they are the ones that exist in snow globes. We're in the process of putting other calculated cross-sections in snow globes to be able to play with them. As far as the cross-sections go, the lines are a little thin. The red line there is the 1N charge current rising above other things, and the 2N charge current, and then the neutral current lines below. Inverse beta decay is down here. So they are high. What we can say about these unmeasured cross-sections is that the thresholds are known, of course. There's less theoretical uncertainty near threshold and more as you move away from threshold. And in 2006, Natalie Jakowitz and Gail McLaughlin sort of parameterized this a little bit, produced this plot. This is the flux average cross-section or folded cross-section as a function of the mean energy and for different possible choices for the pinching parameter, which characterizes the energy spectrum. So basically, you pick an energy and then you look at the width of this distribution, and that's the uncertainty in the flux. It's substantial. Gail characterizes this as it's not well known within a factor of 10. That's the combination of the flux and the neutrino temperatures. So that's our first risk, is the uncertainty in what we would actually see if a supernova happened at a given distance, basically coming from the vertical width of that distribution. I'll talk about the mitigation, what we can do about that later. Oops. So, HALO, the existing detector at SNOLAB. HALO stands for Helium and Lead Observatory. It's, wrong button. We use some recycled lead to make this happen, and the beautiful helium-3 detectors from the third phase of SNO. It's located underground. It's a very manageable sized detector underground at SNOLAB in that position. It contains 79 tons of lead, has been operating for the last 5.5 years, participating in SNOOS for the last 2 years, has been simulated, calibrated, and is well understood, and we have many redundant systems in place, because if you only have one job, you don't want to be off when the next supernova happens. We've recycled the SNO NCD detectors, these beautiful, very low background detectors. And the lead comes in sort of 32 columns, and in each column of lead, we've put an assembly of 4 of these detectors. So 132 detectors, 2.5 to 3 meters in length. We've coupled them up. We have 64 channels of readout for this. We detect them by, of course, neutron capture on helium-3, produces a proton and a triton with 764 keV of energy. We see here, this is a plot from SNO, the full energy peak, and some tails. The tails are due to either the proton or the triton hitting the wall of the detector and some of the energy being undetected. Depending on the background, you see beta Compton events coming in, perhaps even overlapping some of the tail of the distribution. And if you count long enough, you can, these 3 spectra are 3 separate things just superimposed. There is a background due to alpha contamination, alpha emitting contamination on the inner surface that lies there. Underground in SNOLAB, we basically have no cosmic rays to worry about 4,000 fast and 4,000 thermal neutrons per square meter per day in the underground environment. There's also some tritium in the detectors, but we set our threshold above that, and it's at a low enough rate we don't need to worry about pileup. Just to tell that the detector is on, because the rates are so low, we set the threshold so that the whole detector counts away at 5 hertz, so we can tell that it's operating. The rate of neutrons that we see from various backgrounds is about 15 millihertz, which is about 1 neutron per minute or 1 neutron per channel per hour. And I have a breakdown here of where that comes from. It largely comes from leakage through our shielding. We didn't have to go to excessive lengths for the shielding because this is a very workable background for detecting supernova. We did, I think, a very good job of calibrating the detector with a californium-252 source. It's a spontaneous fission source, a very low activity one that we use, about 20 spontaneous fissions per second. And with our low background, I mean, this turned out to be perfect for us. We have a scheme for extending the window for counting the number of neutrons that ensures that we count an integral number of spontaneous fissions. And if we fit the distribution that we measure, which is of course a very sensitive function of the efficiency, if we fit that with single fission, double fission, and triple fission events, we get good chi-squares and a good fit. And because we're fitting the multiplicity distribution, we don't need to know the strength of the source. We fit that at the same time. We did this in 192 positions throughout the volume of the detector. There's 192 points displayed here. This is as a function of radius with efficiency on the vertical axis. At the center of the detector, we're roughly 50% efficient. And as we go out, if the detector were spherical, that might be a nice smooth curve. It's rectangular, so it has structure in the middle. This matches very well with the Monte Carlo simulations that we did within a few percent, but we don't use the Monte Carlo except to extrapolate from the 192 discrete points to a volume averaged source, such as a supernova would be. So there's redundancy built in the power, in the networking, in where we get our time, rather standard stuff. We only have 64 channels. We could have done this with one low voltage power supply, one high voltage supply, one VME crate, and a single computer. But then we would have multiple sources of failure that would take the whole experiment offline. And it is in a remote location, and it can sometimes take days to get back underground to start addressing things. So we split the detector in half and did a lot to build in redundancy. So we even have 2 data acquisition computers that every 2 days swap control back and forth and are always watching the other. And if one fails, the other one just picks up and continues. If a VME crate loses a power supply, the experiment reconfigures itself automatically and continues. So we always have at least 50% of the readout happening. As far as snooze goes, this is the response of the detector. This is the cumulative density distribution of stars in our galaxy. And for 3 different assumed temperatures and pinching parameters, this is the probability that we would see an event. Clearly, it is not 100% for any neutrino temperature and for any distance. Okay. We knew from the very beginning that 79 tons was a small supernova detector. We always wanted to build a larger one. It wasn't ever clear how we would do that. That's where HALO and kiloton comes along. I think I need to accelerate. There's a whole bunch of reasons why we're interested in supernova that you're roughly familiar with. We're concentrating on, it's our premise that nu E bar sensitivity cannot tell you everything, that there's some value to this complementary sensitivity that we offer. We're gearing up, working on studies for how we can take advantage of this complementary sensitivity. It's fairly obvious that if you want to see the nu E burst, you need nu E sensitivity. If you want to measure the nu-E temperature relative to other temperatures, you need nu-E sensitivity. And you know, the observation of a non-thermal neutrino spectrum, again, requires sort of things that HALO can offer. The nu-E to anti-nu-E fluxes are implicated in the R process, providing the neutrino-rich environment for that to happen. And with two thresholds, effectively, we can measure this pinching parameter, this shape parameter. And that's been worked through by Christina Volpe and one of her students. And I'll just show that here. So this is a plot from their paper. It's effectively a legend. We don't have time to worry about the details, but there's an allowed parameter space. And here is a Monte Carlo study of how well we can really exclude some of that parameter space or select some of that parameter space. So the ellipses here are not 1, 2, and 3 sigma ellipses. They're all 90% confidence limits, but for different efficiencies that the detector may have. And you can see there is power to eliminate models and part of that space. So with the decommissioning of Opera, there's 1,300 tons of lead that have been freed up, and our idea is to scale up HALO, keeping many of the same principles and what we've learned over the last years. That's almost a factor of 13 in mass, and we believe we can do much better in terms of the efficiency. With HALO, the average efficiency was 28%. Our simulations are showing in excess of 50. So this is a significant increase, and we believe worthwhile doing. The second risk is that we don't actually achieve this, what we're currently seeing in simulations. So I'll save that just to the end. We have done a lot of simulations trying to optimize the geometry, the performance of the detector, really concentrating on the core, which is a volume of lead with holes in it and detectors and a bit of moderator added. We've played with many things. Constraining the total amount of helium-3 to be 10,000 liter atmosphere is about 7 times as much as was used in HALO at SNOLAB, and 1,000 tons of lead. And we've played with the overall shape, the number of detectors, the groupings of detectors, the material in the walls of the proportional tubes, the thicknesses, moderator, et cetera, et cetera. And we currently find around 53% to 55%. None of this includes consideration of backgrounds, of noise, other signals. And that represents the third risk, that if we assemble the detector and find that the backgrounds are effectively higher, that would inhibit us from participating in SNOOs. So the detector looks roughly like this conceptually. Lead core, 4.3 meters by 4.3 by about 5.5. Almost 800 counters here, 5.5 meters long. They're segmented, 3 joined together. About 8 millimeters of moderator around each, and we assume nothing else in that lead volume for the moment. There's a graphite reflector, some shielding on the outside, and we have a couple of items that we're still looking at for the final optimization of the core. We're just about set, and we're going to be interacting soon with engineers at Gran Sasso and getting a feeling for what the outside can look like. I'm going to go 2 minutes over time. So we're also looking at detector R&D for the neutron detectors. We have the NCDs from SNO were much better really than needed. So we're looking at a commercial production for these detectors. Really, there isn't another option. It's 4.3 kilometers of detectors at the moment. And so we have options in terms of changing the material of the wall from stainless steel to aluminum that would reduce this beta gamma tail down below the tail of this distribution. HALO used the trick of shortening the integration time in the ADCs. The beta gamma traces tend to be longer, and so we're less efficient at collecting the charge from them. That tends to push them off as well. And if we increase the fill gas pressure, we can make the proton-triton tracks a little shorter and fewer of them hit the wall, and that moves events from here into the full energy peak. So, last slide. These risks, the uncertainty in observing in what we would actually see for a given supernova distance. We can't do anything about what the neutrino-led cross-section is. We can't do anything about what the temperature of the supernova neutrinos are going to be. What we can reduce the uncertainty by making a measurement of the neutrino-led cross-sections, and we are part of the coherent experiment, and the plan is to do this in the near future. Not achieving the neutron capture efficiency, we think we have a lot of experience gained from HALO. We also have HALO as a test bed that we can put our detectors in and make various measurements for prototypes. We're continuing with our Monte Carlo development. We have been using Geant 4. We need to use MCNP as well to be a little bit more certain about how things are going to work out. And the background sources, again, compared to a double beta decay or a dark matter experiment, this is rather easy. We need to pay attention, but we don't anticipate any problem in developing a set of specifications that are fairly easily satisfied, that guarantee when we assemble it, it actually works. Thank you. Oops, wasn't the last slide. That's the status. I'll leave that up there.